Hello everyone. Hello. Good evening, Janvi. Hello, Hazel. Good evening, Sravanti. Good evening, Shubham. Join in, join in. Today we'll be talking about graphs. We'll talk about some popular algorithms, DFS, topological sorting, Kahn's algorithm, and Dijkstra algorithm as well. So join in. Good evening, Utkarsh. Hello, Junaid. Hello. Good evening, Hareen. I hope the yesterday's session I hope the yesterday's session was clear to all. We talked about how to represent graphs, uh, w- how to formulate a graph problem, because a lot of times you will not be given a graph, you will be given just a problem statement and you have to create it in a form of graph problem, right? I guess we talked about, I gave one example where we were talking about friendship, and I think you guys must have got a decent idea how to form any problem in the form of graph problem. Let everyone join in. We will begin shortly. Good evening, Aarti. Good evening, Bhavika. Good evening, Akshita. Good evening, Zahida. So those of you who have joined just now, let me repeat. Today we'll be talking about more graph algorithms like DFS, topological sorting. We will be focusing on Kahn's algorithm in topological sorting. It's a very easier algorithm for topological sorting. And why Kahn's algorithm? Because it's easier to understand as we have done BFS, right? So I think before DFS we will do Kahn's algorithm only, because it's easier to understand after doing BFS. You need to know a little bit of BFS. So I think we are fresh in our memory when it comes to BFS. So I think before doing DFS we will do Kahn's algorithm. Good evening, Dev. Good evening, Komal. Okay, so I think we should begin. Oops. I hope my screen is visible to all. So before doing DFS, let's start with topological sorting. So what is a topological sort? It's pretty intuitive, honestly. The one vertex which comes before every other vertex should come first. That's it. Like, to give you a very simple example of it is this. The topological sort of this is this. This is the topological sort. You see, one comes before two and two comes before three. This is the topological sort of. I'm honestly not very sure what will be the formal definition of a topological sort. Okay, they have given a mathematical definition for it. Yeah, we can formulate it as well like that, but I feel like it will be confusing. So मतलब बहुत ज्यादा भारी भारी शब्द यूज कर रहे हैं वो लोग, जैसे कि एक शब्द लीनियर ऑर्डरिंग. You can understand it like a linear ordering is basically a permutation. So any permutation in which u comes before v if there is a edge from u to v. Okay. So let me give you an intuition. If this is your graph, right? So both of these are a valid topological sort because they satisfy this condition. uv if u comes before v. See, there are only three pairs here, right? So 1 2, there is no edge in 1 2, so that condition does not apply on 1 2. 1 and 3, there is an edge going from 1 to 3, and 1 comes before 3, so it's valid. Uh, 2 and 3, there is an edge going from 2 to 3, and 2 comes before 3, so it's also valid. Hence, we have checked all the three pairs, and it's valid for all. So this is a valid topological sort. Same goes for this. 2 and 3. 2 comes before 3, and there is a directed edge going from 2 to 3, so it's valid for 2 and 3. For 1 and 3, 1 comes before 3, and there is a directed edge going from 1 to 3. Hence, again, it's valid. And from 1 to 2, there is no condition because there is no edge. So hence, this is also a valid topological sort. So for one graph, you can have multiple valid topological sorts. So there is one more type of problem you must have seen. I encountered it in, I guess, 1 month before or 2 3 weeks before it came in lead code contest that give all valid topological sorts. So do you understand that problem can be formed as one problem because there are many possible topological sorts for a graph. There are multiple possible topological sorts. Hello Soham, hello. So just to catch you up, Soham, we are talking about topological sorting today. Uh, we are not skipping DFS. We will talk about DFS. We just chose the topic of topological sort because the algorithm we'll be talking about is Kahn's algorithm, and it's very much influenced by the idea of BFS. So yeah. Good evening, Jyoti. Good evening. So I hope it's clear to all. Let me just give you one. Can you guys give me a topological sort for this quickly? Give me a topological sort for this graph. Till then, whosoever has any doubt in previous graph sessions, I can ask because it's very important to clear this topic because this topic is asked in many famous MNCs and all. Star mesh processor topologies. Hmm. The thing you're talking about, Saurabh, is like the famous graph topologies. Like, um, for example, this node, if all the nodes are connected to one node, this type of structure is known as star topology, right? And a bus topology is everything is connected into a linear chain. This is a bus topology. So what you are talking about? This is I hope yes. 3 4 2 1 5. Okay, quick, everyone. First, in order to understand a topic, in order to code it yourself, you first need to understand the algorithm by yourself, right? So try to form a valid topological sort for this example. Then we will talk about how can we write a code, how can we make our computer to answer this problem. First, we as humans should be able to answer this problem, right? So be quick, try to come up with a valid topological sort. Let me make it a little tough. Okay, do this. Come on, quick. 4, 3, 2, 1. Yes, exactly. 3, 4, 2, 1. Exactly. So I hope that this is clear to all. I hope that there is no confusion um, in this definition of the algorithm, right? Definition of topological sort. Sorry, we have not discussed any algorithm till now. I hope there is no confusion. If there is any, please mention it in the chat. Okay. So let's discuss one algorithm for this. So this is I I mean I took this snip from GFG, so you guys can look into it. They also have a very nice example of how they are calculating the topological sort. We will see it. We will see it if we have time. Then okay. So mm, so the algorithm we'll be talking about for is Khan's algorithm. And look, this will make life pretty simple. This will make life pretty simple. Trust me. Like think about it. What should be the first element in your topological sort? What should be the first element? It's quite intuitive that the first element should be one with no incoming edge, right? That should be the first element, right? Because think about it like this: no element can come before that element. Because what was the condition of valid topological uh, pair? U comma V is a valid pair if there is a uh, directed edge from U to V. So U always comes before V if there is a directed edge from U to V, right? So by this definition, trivially, for any edge with no incoming edge should come first, right? I hope it's clear. So Khan's algorithm is actually very intuitive. What you do is you kind of run a multi-source, uh, BFS. You declare a queue, and first let's say that you have an in degree array which have in degree. So I hope everyone knows what in degree is. If you don't, then let me like give you an idea. A number of in degrees on this vertex, how many incoming edges are there? So for this, the answer is 2. For this, the answer is 0. For this, the answer is 0. For this, the answer is 1. For this, the answer is 2. For this, the answer is 1. Okay. This is the meaning of in degree. So assume that you have an in degree array. Let's make a queue now. Insert all elements with in degree equal to 0 into q. Do the following. Okay. No, no, Akanksha, it will happen. It will happen soon. So um, try to focus here. Attendance. Uh, it's not that important. Um, so what you do is for every element for no, like I'm not talking in mathematical terms. Um, int current equal to q dot current q dot pop. Okay, so you just take the one element from q. Now see the adjacency for this. For int j, for let's just not talk about. Now decrement in degree of v such that v belonging to adjacent of current by 1 if any v such that in degree v equal to 0 push into q. Okay, do this. Now order of pushing into q is a valid topological sort. Okay, so let's just talk about this. Okay, let's just talk about this. um 0 0 1 2 2 1. Okay, and this is my topological sort. Now you put 0 and 4. You see let's say you first pop 0 from the queue. You see the adjacency of this. Okay, you remove, you decrement it by 1. Okay, maybe let me just show you how it's done. It's 2. You decrement it to 1. Okay, nothing happens. Okay, you pop 4. Now you decrement it by 0. Okay, now you see uh, this has become 0. So you insert it in the array. Okay, now see you have already popped 0 and 4, so only 5 is left. You see the adjacency of 5, which is 2 and 1. You decrement the in degree of 1 and 2 and see if any of them reaches to 0. So again decrement this and decrement this. Again see this reaches to 0. So oops, this should have been 4, right? This should have been 4. Okay, now you have already popped uh, 0, 4 and 5. Now you pop 1 and you see the adjacency of 1. It's just 2. Okay, so you pop You make it, and you see that this has become 0, so you add 2. This in degree of this has become 0, you add 2, and now you pop 2, and you notice that this will become 0 because 2's adjacency is this. It becomes 0, so you add 3. This is a valid topological sort for this example, right? And notice one thing. Notice one thing. If no valid topological sort, then this implies cycle. There is a cycle in the graph. Just give me a second. Okay, I hope uh, that this is clear. If no valid topological sort, this implies there is a cycle. Is there any doubt in this? Is there any doubt you guys can ask? See, from where did I think I algorithm. This is a very interesting. You can see it clearly. Look, yes, Saurabh, yes, I will try to recap it a bit. So this will act as a recap. Okay. Um, See, how to apply Kahn's algorithm. First, I hope my pointer is visible. Uh, yes, it's visible. Okay, so see, you first figure out the vertices with 0 in degree. Okay, I hope Kahn's algorithm is clear to all, right? Uh, it's not clear to Tanya and Saurabh. Okay, uh, I will repeat a bit. So first you calculate in degrees like we did. Now you start from the vertices with 0 in degree, right? And it is quite I explained to you why, because the definition of a ordering, what was the definition of a valid ordering? See, what was the definition of a valid ordering? This was the definition of a valid ordering, right? And it says u comma v is a valid ordering if there is a directed edge from u to v. So intuitively, there is no directed edge towards the vertices with 0 in degrees. So they ideally should come first in the topological sort. They come before every vertex because they have no in degrees. And from there we are starting. Think of it like this: you are removing the part of the graph with 0 in degree. You are removing this part. Think of it like this. Okay. Then Can you imagine this? You remove this in degree from 0. You remove this part having 0 in degree. Okay. Then you see this. See this graph. See this graph like this. See this graph like this. Now this has 0 in degree, right? This has 1 in degree. This has 0 in degree, right? Now again remove the part with 0 in degree. Now see the graph like this. Again, this has 0 in degree, right? So remove this part. Then again see the graph like this. Again, clearly this is the base case, right? This was the definition. This was the definition of a valid ordering 2, 3 is a valid ordering if and only if there is an edge from 2 to 3. Okay. Okay. Then you remove this. Then you reach here and see the order of removing. You store this order, and this order is the topological sort. I hope now it's clear, right? So try to think it like this. You first remove the part with 0 in degree. Now this is the graph. Again you remove the part with 0 in degree. Now this is the graph. Again you remove part with this 0 in degree. Now this is the graph. See sequentially. Okay, now is it clear? I will come to the fact. How did I conclude that if there is no valid topological sorting, then there's a cycle. I will come on to that. First, tell me if the core algorithm uh, of computing a valid topological sort is clear to all. Okay, I think it was not clear to Tanya and Saurabh. I hope it's clear. Now think about it. Think about it. Let me take an example of. Let me take a simple example. Let me take an example. Okay, clear to Dev. Okay, Zahida, it's clear. Akshita, it's clear to them. I hope it's clear to everyone. Now let me explain you this statement. This statement is very useful, right? Because you must have seen detection of cycle is very important. Detection of cycle is very important in many cases, right? You will study databases. In databases, there is a thing known as conflict serializability. Now I'm not going into that. It's just a concept of how you basically how can you ensure your database works correctly, and there is an application of detecting cycles. Okay, it's not clear to Deepika, I guess. So Deepika, can you please tell me where it's not clear? I think, see, um, um, see, what you do is you first figure out the nodes having 0 in degree, right? Why do you do that? That is because the answer is hidden in this definition. U comes before V. I hope there is no problem if I speak Hindi here. If there will be a problem, please point it out. देखो, कोई प्रॉब्लम नहीं ना, अगर अगर हमारी डेफिनेशन क्या लीनियर ऑर्डरिंग की कि वन एंड वैलिड लीनियर ऑर्डरिंग, अगर अगर वन पहले आता है टू से और वन पहले आता है टू से, इस पूरे जो सेंटेंस है कि वन पहले आता है टू से, इसका मतलब क्या है इन टर्म्स ऑफ ग्राफ? कि देयर इज अ डायरेक्टेड एज फ्रॉम वन टू टू, राइट? थिंक ऑफ इट लाइक दिस, लाइक अगर तुम्हें वन से थ्री पे जाना है तो द एरो इंडिकेट्स, राइट? तुम पहले वन पे जाओगे, फिर तुम टू पे जाओगे, फिर तुम थ्री पे जाओगे, राइट? सो व्हाट इज द डेफिनेशन ऑफ वैलिड ऑर्डर इन टोपोलॉजिकल सॉर्ट? दैट u कॉमा v, या फिर पे बात नहीं करते हैं, क्या बोलते हैं, सिंबल्स पे बात नहीं करते. Let's talk in terms of numbers. 1 comma 2 is a valid sorting if there is an edge from 1 to 2. So that's the reason why you take first the vertices with 0 in degree, you remove them, then you take, when you are removing them, remove them completely. Removing a vertex means remove the edge, uh, also remove the edge including that vertex. So you also remove these connections, because after removing this part of the graph, only after removing this part of the graph will you get this vertex as a 0 in degree. If you don't remove this edge, then there is no 0 in degree. The in degree is 1. So you have to also remove the edge of the vertex. So see, you first remove the vertex with 0 in degree, then you remove next vertex with 0 in degree, then you remove the next vertex with 0 in degree. So see, you're trying to do this sequentially, right? So that's what Kahn's algorithm says. It's quite simple. Um, Now see, this is quite. I feel like this you guys will be able to catch this concept really quickly. This Kahn's algorithm does not work on this graph. Why? Because the first thing was before entering in this loop, insert all elements with in degree 0. There is no element having in degree 0 in this. Look closely. 1, 1, 1. Right. There is no element with 0 in degree. And similarly, uh, think about this. That okay, here maybe we are getting a feeling we can apply Kahn's algorithm. But think about this. At the first iteration itself, the Kahn's algorithm kind of breaks. Kahn's algorithm breaks because again you detect a cycle. 1, 1, 1. See, there is no vertex with 0 in degree, and hence you fail to proceed further. Right. So if no valid topological sorting, then there exists a cycle. Right. And I feel like it's intuitively clear to all that there is no meaning of topological sort if we are talking about undirected edge, because there is no meaning of saying u comes before v if there is an undirected edge between them. It's a bidirectional edge, right? You cannot say anything. You can imagine a undirected edge like this. An undirected edge can be imagined somewhat like this. It doesn't make any sense to talk about topological sorting in terms of undirected edges. So I hope topological sorting is clear to all. It's a very interesting concept. We talked about an example. We talked about the algorithm. Uh, Let me see. I hope now it's clear to all the people who are asking doubt in this problem. Let's try and solve this. Okay, just let me see if I can find a more interesting problem for topological sort. Okay, due to the scarcity of time, I will just, I don't like doing this, but I will just show you the code for this. Okay. So the problem says like you are given an array prerequisite where prerequisite I is AI, comma bi. Okay. Let me. Yes, Dave, you are right. I mean, I was planning to solve some really nice problems, but I feel like due to less time, it will be tough. It's tough to cover because graph is in terms of theory, it's a little big topic. Okay, so you guys can mark your attendance. Part two, I feel like we need to see part two. If there will be a plan of taking part two, then obviously we will be discussing some really fun and but really tough topics there. So I will expect that mm, you guys actually try to practice what we have talked till now. You know, a lot. Actually, see, Saurabh, we have with terms of in terms of interview perspective, we have actually talked what they can. We have talked enough. They can ask you in terms of interviews. What I was saying was a bit of problem solving part, like um, because it's fun. Or maybe I can give you some resources from which you can practice towards the end of the session, towards the end of the boot camp. But yes, so let's try to solve this problem. I hope it's visible to all. The problem says that there are a total of num courses you have to take labeled from 0 to n minus 1. You are given an array prerequisite where prerequisite I is equal to ai comma bi, indicates that you must take course bi first if you want to take course ai. So now see, try to formulate this graph problem, right? They have given you prerequisites. They have given you prerequisites such that they have given you prerequisites such that u comma v, I mean course AI comma BI. So you should take course BI before you take course AI, right? So try to imagine an directed edge from B to AI, BI to AI, right? Try to imagine BI to AI. Now try to formulate this. So essentially what they have given you is they have given you the edges. They have given you the edges, right? So for example, if I give you one instance of this problem can be this 1 comma 2 and 2 comma 3. So this 1 comma 2 can also would have been given you like this um, DSA into DSA before DOA, um, and then after DOA you do advanced DSA, right? So that's how you map it, like DSA first into DSA, then you do Okay, there was. Oh, sorry. We kind of DSA because there is an edge from this piece. So you need to do DOA, then first DOA, then advanced DSA. So DOA, then advanced DSA. So a valid topological sort must be first you do DSA, then you do DOA, then you do advanced DSA, right? Right. So you can formulate this problem like this. Okay. So you understand that the in degrees will always be for the first part because first element of this uh, vector, because this is the edge. This is how we are forming the edge from DS to DOA, from DOA to advanced DSA. This is the definition of the problem, right? So see clearly, I have first I've created the array, and then I am this is for in degree vector, right? Now I initialize a topological sort and a queue. Push vertices with 0 in degree in queue, right? Do this. Now, if the topological array, topo array is the size of that array is n, then there is a valid topological sort, else there is not. We already talked about it, right? If anywhere your Kahn's algorithm stops before giving you n vertices, the total vertices, then there is a cycle in it. So the problem was if you need to give a you need to tell if there will be a valid topological sort or not, right? This is a simple problem of just how to apply Kahn's algorithm. This video will be on YouTube. I'm not writing it by myself because I feel like given the time constraint, it will be a total time waste. It will not be a time waste actually. Honestly, it feels good when the other person is typing with you, but uh, considering the time constraint, I feel like maybe it will be better if you will have any doubt in the terms of code. You can see this video by going back to this part, right? First, understand this. Try to understand this algorithm. Implementation can vary from problem to problem, like Python to C++ and to any other problem, right? I have done my codes in C++. I will also try to share these codes with you. Any other doubt to anyone in topological sort? You guys can mention it in the chat. Any doubt, any kind of doubt you have. Okay, if not, then we move on to one more very interesting algorithm, which is the Dijkstra's algorithm. Okay, And constraint not negative weights. I hope that everyone has marked their attendance. But this is the only constraint. It is not for negative weights. Okay, let's. Okay, maybe I can just show you. So Jack's algorithm kind of works like this. There is a source given to you. Okay. Let's just take the source given to you. Let's say in this case the source is 0 and there are some edges given to you as well. For generality, assume not assume, like for generality, I'm saying that in Dijkstra's algorithm, you try to make a functionality such that in the queue, you're always taking the vertex which is reachable in the smallest amount. Now, by what do I mean by smallest amount? By in the smallest cost, and the cost is obviously this. And how do you do that? The answer to that is priority queue. What priority queue does is, I will just tell you what priority queue does. It always gives you the minimum, right? Minimum. So you can tweak it with respect to your needs. So in this algorithm, we try to take the minimum of the cost. We minimize the cost function. So cost function for this will be 0. You go and this cost function of this becomes 4. Again, you take the minimum, which is 4. You make the cost function for this is 8. This as 6 and this as 7. So again, you go towards the minimum cost function, which is this. You go here, you see 6 plus 2, which is 8. Already 7 is present, you don't update it. And you go back, you see 6 plus 2 is equal to 8, but 4 is already present, you don't update it. Again, you go to the minimum one, 8 plus 4 is equal to 12, but 4 is already present, so you don't update it. And again, 8 plus 1 equal to 9, but 7 is already present, so you don't update it. That's how a valid Dijkstra's algorithm works. Let's try and jump onto how do we. See, you guys can refer this blog. It is a really nice blog for Dijkstra's algorithm. They have taken some quite nice examples for illustrating Dijkstra's algorithm, and they have also explained this algorithm quite nicely. Okay, so towards the end, I would like to also tell you all how you can practice this. We have talked about a lot of concepts. Try to practice here. This sheet is very nice from Striver sheet, they call it. You can practice from here. We have kind of talked about a lot of problems for from here only. You must have seen we talked about climbing stairs. In 2DP, we talked about unique path, subsequences. Uh, in strings, we talked about longest common subsequence. In LIS, we talked about longest in green subsequence. So they are part of uh, the pattern. And you can also practice graph problems from here. You can practice BFS, DFS from here. Um, you can also practice topological sort problems from here, and also the shortest path problems. Due to the scarcity of time, obviously we cannot solve these many problems. That's why I tried to introduce you to the concepts. I tried to solve one problem for every concept. Uh, I expect you all to practice them on your own, because you guys can see like there are around 56 problems for DP and 54 problems for graph. So I cannot solve 110 problems in like 5 hours, but uh, try to practice this on your own. You can solve this these two sections like dynamic programming and graphs. They will be really easy. And after doing graphs, you can also try doing some problem of trees. And those of you who want to like dive deeper into the problem solving, you can also solve this CSES problem set. Dynamic programming. This is a really nice problem set. They have recently added some problems. You can also solve this graph algorithm part. Every problem you will see in the world of data structure algorithm is inspired by CSES problem set, because they have done a really great job in incorporating every core idea of every algorithm. So I would say the first, try to practice from here. Try to practice graph and DP from here, and only when you have practiced enough, try to do this. This is the real fun. Like you will enjoy these problems. So you can just search Dave like CSES problem set. You will get this. You will get this right away. And even for Striver sheet, just search it and you will get the link right away. I guess. Yes. So try solving these. I hope you guys learned something from this boot camp. You learned how to tackle DP problems, how to decompose every DP problem into a group of different sub problems. I hope you learned the pattern of DP on strings, DP on subsequences, 1D DP, 2D DP. I hope when we came onto the graph, I understand there was a lot of theory. It was not that much theory when we were studying DP, but you know that makes graph easier than DP, right? When there is so much theory, then you kind of then interviewer kind of becomes predictable, right? If you have theory, just imagine you don't have any theory, and then you are asked to sit in an exam, then it's unpredictable, right? But if there is theory, it always, the ball is always in your court. You can always prepare well. So graph is not tough. It's just that it is a little lengthy. It's not tough. Trust me. Um, so try to solve these problems. I hope you guys enjoyed the boot camp. Um, Thank you to all who all have stayed till the last session. I was expecting that people, regular people, will the watching will drop for the subsequent session. Uh, I'm sorry for, because of the scarcity of time, I was not able to solve a lot of problems with you. But I'm sure I have covered the uh, covered the majority part. Like I tried to cover every pattern for every problem, for every set of problems. Like see topological sorting में भी आप लोगों को वही पैटर्न पे प्रॉब्लम्स मिलेंगी. बीएफएस में हमने रॉटन ऑरेंजेस करा था. यू विल गेट पैटर्न ऑन सेम पैटर्न. वी डिड मल्टी सोर्स आल्सो. एंड डीपी में भी आई थिंक तुम लोगों को लग रहा होगा कि हम लोगों ने लॉन्गेस्ट इंक्रीजिंग सबसीक्वेंस ही करा, तो हम सबसीक्वेंस कैसे करेंगे. थिंक अबाउट इट, डू दैट प्रॉब्लम, यू विल रियलाइज वही पैटर्न है. स्ट्रिंग्स में भी हमने ट्राई टू डू दैट होमवर्क प्रॉब्लम ऑफ पैलिंड्रोम. यू विल अंडरस्टैंड कि लॉन्गेस्ट कॉमन सबसीक्वेंस में जो आइडिया था ना, वही आइडिया है उसमें भी. So try to incorporate, because obviously I cannot do all the problems, right? Topological sorting वापस problems करने की try करो. So yes, and all the very best to those who are giving code courses contest today. I think there is Div 3 today. Yeah. So yeah, see you all in the next session, next boot camp. Thank you Akshita, thank you Saurabh, thank you Saranjeet, thank you Gautami, thank you Devajyoti, thank you Dev, thank you Saurabh. Thanks a lot guys. Bye.